7.3 is on properties of Laplace transforms. So we'll go over a few theorems and proofs, a couple examples. So I just wrote down the Laplace transform right here, how it's defined, of course. This first one is called the translation property. And so if L of f of s is equal to f of s, right, it basically exists for s greater than alpha. That's all standard. Then if you basically put e in here like this, then this is equal to f of s minus a for s greater than alpha plus a. So it's pretty straightforward proof by just plugging in the EAT. So it's basically like saying this is like your like h of t equals EAT f of t is essentially what that's saying. So I wrote up most of this. So assume that the transform exists, right? So when I say that it's element of R, it means it basically exists for alpha, for s greater than alpha. That's standard. Then the Laplace transform of e to the at f of t of s is equal to the integral 0 to infinity e to the negative st. That's standard, or that's above. And then you're just putting e in here, e to the at f of t dt. And so you just combine the e's and essentially you have it. I mean, it's really it. So it's equal to the integral of 0 to infinity. And so that's just e to the negative s minus a, just simplifying a little bit, f of t dt, which equals, so that's the same form as above, right? It's this form, but instead of s minus a, you have just, instead of s, you have s minus a right here. Everything else is the same. So that equals just f s minus a. Okay, and that would be true for s greater than alpha plus a. So just, I mean, initially you'd have, right, you'd have s minus a greater than alpha, like that, and then you just add a, and so s, it has to be greater than the sum. Okay, let's look at an example. This is not this property above, but just another example. So determine, well, actually, no, it is up from above. Anyway, here it is. so determine the Laplace transform of e to the at sine of bt of s. So we're going to use one of the formulas we've already looked at to do this. So what we want to look at first is that the Laplace transform of sine of bt of s is equal to capital F of s. And that is from above. See how far back we have to go. It's from this table right here. So sine of bt is this. And so we're going to use this, and then we're going to translate the s. So that's the technique. So we're not going to actually evaluate that. So we have then f of s is, from that table, b over s squared plus b squared. And then applying the translation property, And this is still true for S greater than alpha. So by the translation property above, okay, let's mark that. So this is the translation property. You have that Laplace transform of e to the at sine bt of s is equal to f s minus a. So it's like it's automatic, right? So then we can write that into the formula b over, so your s now becomes s minus a quantity squared plus b squared. So you're going to be looking for, when you simplify these things, this form, this denominator form is how you'll start interpreting things. Maybe complete the square of some sort to get it into this type of form. And then we can evaluate either direction. Okay, let's continue. Next is theorem 4. Let's see which one's that. So this is the f of t, this is f prime. So when you look at the Laplace transform of f prime, what does that equal? So I'm gonna grab the statement over here. Which is down here. So there's theorem 4. Paste it in here. All right, so theorem 4 states this. Continuous on, this is all standard, and f prime is piecewise continuous on AB, 0 to infinity. Okay, both exponential order alpha. Then for s greater than alpha, you get this. So you get Laplace transform of f prime of s is s f of s, L of f s minus f of 0. It's kind of a strange result, maybe. I don't know. So let's take a look at that. Let's see. So, hypothesis stuff. You're going to assume f is continuous, f prime is piecewise continuous, etc. Okay, so all that's, we'll skip some of that for now. So then let's just take a look at the form. So you get Laplace transform of f prime of s is equal to the integral 0 infinity e to the negative st f prime of t dt. Okay, then that's equal to the limit as n approaches infinity, integral 0 to n e to the negative st f prime of t dt. So this isn't obvious, but we're going to apply an integration by parts. Okay, so apply parts. So we're going to do integration by parts. This will be my u, and this will be dv. Like that. I think you can read that all right. Okay, so now apply integration by parts. So my u will be e to the negative st, and my dv will be f prime of t dt. And so I'm not going to show all those little details. So do that to this next step, and we get that the limit as n approaches infinity of e to negative st, this is uv, basically, and then we can break up the limit. Oops. So we can break up the limit to 0 to n. So yeah, so that's the limit. So this becomes plus s. So it's uv, and then I'm factoring out the s. I'm skipping a few steps, I think. Okay, then it's 0 to s, e to negative st, f of t dt. All right, and then there's no in there. So that's equal to the limit e to the negative sn f of n minus f of 0 as n approaches infinity. And so the second one just already evaluated. So then that's plus s times the limit as n approaches infinity. Integral 0 to n e to negative st f of t dt. All right, so then continue to work this out. All right, so that's equal to the limit as n approaches infinity, e to the negative sn f of n minus f of 0. And so this is just the Laplace transform of f of t of s. So once you get to here, then this is just the Laplace transform. Okay, so then we want to investigate what this limit does. And so we know that f of t is exponential order. So we want to basically create a inequality. All right, so what we have then is, since f of t is exponential order alpha, we have that there exists an m greater than 0 such that absolute value of e to the negative sn f of n is less than or equal to e to the negative sn, because it's always positive, m e to the alpha n, which equals m e to the negative s minus alpha n. So then when you take a limit, so for s greater than alpha, we have that 0 is less than or equal to the limit as n approaches infinity, the absolute value of e to the negative sn f of n, which is less than or equal to, And so now I'm just dropping it and going and taking the limit all the way across. That's all I'm doing here. Just takes time. Limit n approaches infinity. M e to the negative s minus alpha n. All right, so what is that going to equal, basically? So I'm saying that, so this is absolute values, so it has to be positive. But when you do the limit, what happens to this if s is greater than alpha? Yeah, that has to equal 0. So that limit's 0, and you basically have it. All right, so that means this limit you get, this is your 0, which you just bring over here, and that's going to 0. All right, so that's it. I don't need a conclusion, really. You can state the conclusion next, but we'll save some time. So therefore, you have the statement. You have this. Okay. So this theorem, let's see, what do I got left for you? We'll leave the rest to just take a peek at, well, not the rest of the video, this video. Theorem 5 and 6. And then, yeah, you can look at this one. It shows some concepts that you can take a look at to find the derivative and simplify stuff. So let's bring that over, show it to you. So here's my conclusion, right? I wrote up in my notes, but you don't always have to say that. It's like it's been proven. That's why you see it sometimes see the QED, meaning it has been demonstrated. So anyway, all right, so this is for higher order. All of this will come down to here. It's really this whole page, I guess. All right, so let me bring it back over here. We'll talk about it a little bit. I'm not sure it's going to fit all there. Okay, looks like that fits. All right. So for higher order derivatives, we have this formula basically. So you have the nth derivative of s, then you get this progression essentially. So that would be done by induction on n, not something I want to go over. It's kind of tedious. Something you look over later if you're in math. So you can apply this concept to help simplify stuff. So if you know like this, then you can take the derivative of the function, and then essentially by forcing your b here and here, then you get the next theorem. So you can show pretty quickly. Check this out right here. You can show pretty quickly what is the Laplace transform of cosine bt without actually taking the Laplace transform, because you can multiply this by b on both sides and then divide it out, and you get the formula just by applying the formulas above. So pretty slick there. The next one, theorem 6. So piecewise continuous, and let's see, what was the difference between the two? Oh, this just puts t in there. So instead of putting like e here, they put t to the end. So just another common thing you might see when you do these things. This one I did go through the proof apparently. So let's probably usually when I do this, I mean it's something it's a good proof to go through. It has some properties I'd like you to see, and it's reasonable to go through, to go over. Anyway, let's take